Okay, let's begin. What are we going to talk about today? All right, all right. So you go to a concert, and at the concert, you're moved. Emotionally, you are moved. I mean, the music comes and you feel good. You can feel, you can get into it, you're a part of it. You might even be moved to your eyes watering up a little bit. Sometimes it's so beautiful. And as this is happening, you realize the musicians down below there, or up in front, I think, are all following some sheet music. And that sheet music can be given to different musicians, and those different musicians can look at that sheet music and they can do the same thing. And you wonder, hey, wow, that is really nice. That this emotional response that's evoked from me comes from a pattern that's on pencil and paper. You think about that. It's all up, and you look at the pattern, and it's very complex. And if you're not into music, it looks like, wow, it's just gibberish, isn't it? But the musicians are trained to read that pattern. And then you get out of the city and you go up country at nighttime and you're looking out a night when there's no moon, huh? And the moon's on the other side. And you look out and you see the Milky Way. And you see all the stars. And you see more stars than you can see when you're in the city. That's because the city lights, of course, light up the sky, and the sky's reflecting light. You know, only the brightest stars will show through, huh? But in the country, you see many, many, many. And sometimes you also are moved. You get that sort of emotional, all of a sudden you're connected. All of a sudden you're not quite connected, and you start to wonder. And you wonder what is going on out there. And then you realize there are more stars in the sky than there are grains of sand on all the beaches of the world. Honey, a lot of grains of sand. More stars. Not in your visible view, but out beyond. Many, many. And you wonder, is there a pattern that dictates what those stars are doing? Why they shine? How they move? How they relate to one another? And you know what? There is a pattern. There's a pattern to the whole cosmos. We're going to talk about that pattern in detail. Would you like to see the pattern? I'll put it right up there on the board. Want to see it? Here it is. Dun, da, 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 dun, da, 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 dun, da, da, da. That's it, gang. That's called the universal law of gravitation. And that law of gravitation was developed by guess whom? Isaac Newton. You know what? A lot of people think that Isaac Newton discovered gravity. He didn't. The cavemen knew about gravity. The cave women knew about gravity. What Newton discovered was what? Check your neighbor and see if your neighbor be knowing. In other words, did you get a chance to look through the chapter? What did Newton discover about gravity? Newton discovered that gravity is what, gang? Universal. Universal, you're right. Universal, that gravity extends everywhere. And what this equation tells us, the equation of gravity, just tells us that there's an attractive force, F, between all things. And for any two things, that attractive force depends upon, is proportional to, is related to, the product of the masses of the two things. This might be a planet 1. This might be another planet 2. Those two planets are tugging on each other with a force that depends very much on how much mass they have. But it also peters out with distance squared. As the distance between those planets, or those chunks of matter, or those particles, as the distance between increases, guess what happens to the force? Just what you would expect to happen. Larger or smaller? How many say, oh, it seems to me as the planets would get further and further away, they'd pull harder and harder on each other. Stand up, I want to see what you look like. Nobody say that. But you see, we can say that statement here mathematically by putting this downstairs, huh? As I make the distance big, what happens to the force? Can you see that mathematically? You can see it conceptually too. Far away, less and less effect. So let's see what we mean by this. Mass 1, mass 2, force. I want to teach you how to read this. I have a planet, boom, mass 1. Another planet, boom, mass 2. There's a certain force pulling those things together. Let's suppose mass 1 all of a sudden, I don't know how, but become twice as massive. What would the force do? Be more, less, or stay the same? This tells you be more. If you make this bigger, this gets bigger. Hey, Let's suppose this gets twice as massive. This one gets twice as massive. Then what's the force going to increase to? Check the neighbor. Two times two, gang. Come on. About 4. Okay. You got it? Okay. How about this? A couple of planets. It's a pull, right? Now I'm going to take the planets and put them twice as far apart. Twice as far apart. Everybody knows the force is going to be less. Every fool knows the force is going to be half. But that's the fools. Us. We not fools, honey. What's it going to be when two planets are twice as far apart? Check your neighbor. See if your neighbor can read that. I don't know if you can. How many say the force is going to be reduced to 1/4? All right. How about I take these planets and I move them to 3 times as far apart? This will be your test. 3 times as far apart. Don't say 1/3, because it's 1/3 times 1/3. A 9th. You got it? Can you do big numbers? We're going to see if you can do big numbers. 2 planets, 10 times. 10 times as far apart. Try it. The force is going to be 100th as much. 100. Do you see this? That's the law of gravitation. You know where this law of gravitation came from? Newton's mind, sure. But Newton had some hints. And Newton says he climbed on the shoulders of giants. And one of those giants was a fellow by the name of Kepler, an astronomer type. Kepler, who spent his lifetime making sense out of the data of one of his contemporaries, Brahe. Tycho Brahe spent his whole lifetime gathering data about the planets. And back in the 1700s, Kepler found some very, very interesting things. First of all, Kepler found out that the planets go around the sun not in circles, but in what? Ellipses. And I can draw an ellipse for you, gang. An ellipse can be constructed as such. I wish I knew this when I was in high school in woodshop, when I had to make a coffee table. And I made an elliptical type coffee table, and I thought I was very clever, because what I did is I drew one quadrant of an ellipse on newspaper and cut it out, and then folded it over, traced it, folded over, traced it, folded over, traced it, and I thought I had what was a nice ellipse. If I had known about this, I would have had a better coffee table. I can construct an ellipse very simply. Watch this. You turn the string around, gang. You kind of get the idea. That is an ellipse. An ellipse is a path whereby the distance at any point, like out here, the distance from here to here, plus the distance from here to here, is a constant. That's the definition of an ellipse. Take a math class, you'll learn that. But the string has a constant length, doesn't it? So everywhere along there, it's always a constant. Isn't that neat? And Kepler found out that the planets travel that way. And one of the foci, focus, plural, foci, one of the foci right down here. And that's the sun. See? And he found out the planets go around like that. But most of the planets go around not so eccentric an ellipse, like more circular. If the foci are closer together, like here, and like here, they're kind of close now, yeah? Okay, now the ellipse approximates a circle. Isn't that neat? And when I have both points right together, then I get what? Begins with circle. That's right. And a circle is a special case of an not eclair, ellipse, okay? Yeah, a circle is just a special case of an ellipse. Get the idea. Isn't that neat? And Kepler found that out. And from that, Newton deduced the law of gravity that we see here today. We'll talk more about Kepler's ellipses and the link between here and gravity when we talk about satellite motion. And that'll be pretty soon. What I want to talk about now is this idea here, the inverse square law. The inverse square law is very important. It's important enough that I want you to be able to feel it and see that it makes sense. It looks complicated, doesn't it, to say that something depends upon 1 over distance squared. I want you to see that that's intuitive and that it ought to be distance squared. Let's see if we can develop that. Let's suppose I have here a candle flame. And that candle flame is shooting light out, sending light out, equally in all directions. Oh, except straight down, the candle's in the way. But anyway, the influence of the light goes off in all directions. You will find when you study light that the intensity of light varies as the inverse square of distance. You will find when you study radioactivity that the radioactiveness varies as 1 over the distance square. You will find out magnetism, with a magnetic pole here, that the magnetic field strength goes off as 1 over the distance square. You will find out when you talk about electricity, and you've got a charged object here, that the further and further away you get, the electrical influence peters off as 1 over the distance square. All through physics, you'll see something over the distance square. And I want you to see that that's intuitive. We'll do it now for the case of light. Let's suppose this eraser is a piece of photographic film, and I hold that photographic film right here. There it is, okay? I'm catching light. In fact, a shadow's cast, isn't it? I'm catching all the light that comes in here and out to here. I can't draw this part out here, okay? But that's how much light I'm catching. And let's say I'm a particular distance away, and I'll call that distance to there. Okay. The question is, if I get twice as far away, will I catch less light or more light? Because if I hold it here and I bring it into the darkroom and develop it, the film there is going to be darkened there, isn't it, with a light hit? How about if I held the film twice as far away? Twice the distance. It's about here. Oh, look at this. Out here, this could fit in the shadow. I could get 2 erasers in the shadow. Could I get 2 erasers in the shadow or more? In the shadow cast by this. Some people say, oh, 2, I can see 2, 1 here and 1 there, and that's the end of it. And other people say, no, 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 no. You get more than 2. More than 2 erasers will fill the shadow. See if your neighbor knows. Begin with F, end with OR. 4. Excellent. All right. Because you could get 1 here, 1, and out like this too, see? It's sort of like that, like 3D. So you know what? 1 eraser here would catch 1/4 as much light as if it were here. Do you see that? 1/4 as much, because the rest is going here, here, here. Huh? So 1/4. Let's suppose I get 3 times as far away. That's about out to here. Out to here, is that about right? 1, 2. I'm not sure if it's drawn to scale, gang, but over here I get, look, 1, 2, 3. I can get 3 erasers. So someone say, gee, 3 times as far away, 1/3 the light. Because this would get 1/3, the rest would go up here. 1/3 is wrong. What's the answer, gang? Neighbor. How many got a neighbor not saying anything? How many got an antisocial neighbor today? Sort of a little smug, a little stuffy, little uppity. Point. Who? Check that neighbor. What do they say? How much? It's a 9th, ain't it? Huh? So you get like this. See that? See this eraser? Here it is over here. It's only getting 1/9 the action, because the rest is all coming out here. And so then I could say, what if I put it 10 times as far away? And you guys would say, hey, it's not catching 1/10 the light, it's catching 1 what? 100th the light. Because 10 times as far away, I could have 100 erasers fill up the shadow that this one took. 100 erasers would be required to catch all the light that this one here caught. So the intensity out there would be 100th. Well, guess what behaves the same way, gang? Begin with a G. Gravity. The same way. And that's what we got up here. So it makes sense. Here's the world here. There's gravity to the world. This is a particular mass. And this mass is pulling on every other mass. One mass is out here 240,000 miles away. It's the moon. That moon's being pulled toward the Earth. But the Earth's pulling on the moon. You guys know what else has happened. The moon's pulling on the Earth. That's right. Okay, they're pulling on each other. And it pulls it right around and around and around. You guys are standing right here. And when you're standing right here, you got a mass too. And this got a mass. Take your mass, multiply by the mass of the world, then divide it between the distance between you and the center of the world, squared. Guess what you get? Begin with W, end with 8. Try it. Your weight. That's what your weight is. Your weight is a gravity force. It's a gravitational interaction between you and the world. Between the mass that makes you up and the mass that makes up the world. And that's what it is. Make sense? You feel weight because the gravitational interaction pulls you against the surface. What if we cut out the surface and you're here? Okay? Well, wait a minute. If you cut the surface out, then you'd kind of fall toward this, wouldn't you? You'd fall to it. What happens when you jump off a curbstone for a little bit? Do you weigh anything? What happens when you jump off a cliff? Do you weigh anything? Is there a force acting on you? You're driving in your car, your friend's car, and your friend says, hey, I want to do something different today. And you're driving, and all of a sudden, no, not this different. And as you fall down, is gravity pulling on you? How many say, oh no, gravity ain't pulling anymore. Gravity gonna take a holiday because you is moving. Stand up, I want to see what you look like. Nobody say that. You know gravity pulling on you, okay? But you don't feel it. You know why you don't feel it? Because there's no more support. When you're riding in your friend's car, steady speed, huh? And you're sitting right down, you're scrunching right against the bathroom scales. Those bathroom scales are supporting you, holding you up. Now when that car goes off the cliff, you look down at the bathroom scale, you want to read the force of gravity, but what do you read, gang? You read 0. Because you and the bathroom scale are both fallen together. And so you feel what you call weightlessness. In physics, we say there's an apparent weightlessness because there's really a gravity force acting on you. Okay? But it's like this. I got here this ball. Okay? You're in an elevator. You're in an elevator, and all of a sudden you're holding a ball up like this, and someone cuts the cable. And as you're falling down, it seems to you like someone cut the gravity off. Watch this. I hold the ball in front of my face. I step off, let go, and it's still in front of my face. Okay? Now, why did it stay in front of my face? Now, if you want to try this and you want to really get the effect, jump off a very, very tall building. And as you jump, you go, son of a bitch, hey, there's no gravity act. There's plenty of gravity acting, okay? The thing is, though, you're both falling together, and it feels like there's no gravity. Talk to an astronaut type who's been in orbit. Guess how they feel? The same way you feel when a car goes over a little lump like that. Also, you're not supported for a moment. You feel that little queasy feeling? They feel like that all the time. That's why they bring barf bags. Yeah. It's an apparent weightlessness. It's because everything, your whole environment. People on the space shuttle. You look up in the space shuttle. Your friends say, hey, look at those dudes up there, honey. They got no gravity. They got no gravity because they seem to be floating around. They take this ball out, let it go, and just hover right there. Take a pen out like that. It just kind of floats in front. It looks like there's no gravity because the TV cameras inside are recording that. And they see the astronaut type like that, and they see it floating like this. Hey, no gravity up there. It's a common idea that there's no gravity up where the satellites are. What do you guys say? If you use that equation to guide your thinking, D up there is not very much bigger than it is down here. That D is toward the center of the world. Newton figured that out. When you want to measure the force of gravity between you and the world, you take the distance between your belly button and the distance to the Earth's belly button. That's the center of mass. That distance. And when you go 100 miles high, honey, that's not much more than the 4,000 miles you are to begin with. So they have just about as much gravity up there in space shuttle territory as they do down here. But those video cameras make it look like gravity's been cut off. Much of the public does not understand that. We do, because we are a little more educated than much of the public. Is that true? Do we see that, hey, everything is falling together, huh? It's falling around, around, and gravity is very, very much there. If it weren't there, space shuttle would be long gone. But it falls around and around and around. And we'll come back to that idea when we get to the next chapter. Force of gravity everywhere. Well, let me preface that with a statement like this. How far out would you have to go before the Earth's gravity would be no more? If you go to the far reaches of the universe, is home still pulling on you? Check your neighbor. How many say, yeah, I'm thinking so? How many say, hey, I don't know enough physics yet? Give me a chance. Give me a chance. I don't be knowing. Don't know everything. I don't know enough physics to answer the question if you want to know. Hands. How many say, I think I be knowing enough physics. I know the answer to that question. Hands. Well, Oh, I didn't. Can I do that one more time? I think I caught 2. No, come on, you guys. Yeah, we can see why. Because that equation kind of tells us, doesn't it? Okay. How big do you have to make D before F goes to nothing? And you know what it turns out? Honey, you can make D out to infinity. And even then, as D approaches, any mathematic types here? As D approaches infinity, F approaches, but never gets to 0. So you get out the far reaches of the universe, take that distance, square it, multiply the mass of the Earth times your mass, and you'll get the force that acts on you. Not very much, way, way out, but it's there. Because this holds all throughout the universe. So what did Newton discover about gravity? It's universal. Let's try some more equation reading, gang. Here's the world. Here you are standing on it. And all of a sudden, I don't know what happens. Well, the Earth is all of a sudden twice as massive. Twice as massive doesn't mean twice as big. It just means that it has twice the amount of mass for its size. Maybe all like the iron atoms become lead atoms or something like that. You hear what I'm saying? Let's suppose, this is just a thought experiment again. Let's suppose you're on the Earth and all of a sudden it became twice as massive. What would your weight do? How many say, all of a sudden, honey, you'd weigh twice as much? Show of hands. Suppose you're standing here on the bathroom scale, and for some reason, your mass you've eaten a lot of donuts, a lot of eclairs for a long time. You become twice as massive. Ooh, what happened to the force of gravity between you and the world? Hey, that's easy. More. How much more? How many say, that tells me how much more? Huh? Make one of those twice on the top, the force becomes twice. You see that? So you become twice as massive. Twice the weight. So people that are twice as massive weigh twice as much. Do you see there's a difference between the two ideas? Some people don't. They say, you're saying the same thing. No. How much mass you have is altogether different than how hard it's being pulled by gravity. Because you can take the same mass, take your same mass and go to the top of a mountain. At the top of a mountain, strictly speaking, you weigh more, less, same. Or there's no way to say. What is it? Begin with an L, end with S. Less. And why do you weigh less? Because you made the distance greater. Want me to give you a type of question that wipes out about half the students on an exam that has to do with equation reading? Let me show you what it is. Here's a ladder. The girl right here weighs 400 newtons. It's about 90 pounds. She climbs a ladder that is just as tall as the radius of the world. Up here, she weighs less, more, or the same when she stands on a bathroom scale. Forget the effects of rotation. More, less, or the same. How many be saying less? I got that far, honey. I got that far. Less. Okay. How many say, hey, not only less, I know how much less. In fact, if she weighs 400 newtons here, up here she will weigh, check the neighbor. Here's how far she is away when she weighs 400. 1 Earth distance away. The radius of the Earth away. Distance the radius of the Earth. When she's up here, she's 2 Earth radii away. And you all know, I think all of us, yeah? We all know what the value is going to be up here in newtons. Let's hear it all together. A little louder. 100. I heard everybody say 100, right? Even the wimps, right? There's no wimps in here. But it's 100 again. 100. You see that? You see that? Could you guys have got that under pressure? Could you? Well, maybe under pressure, that's something different. But you see what you do? You just simply say, hey, if this changes, then how does this change? And if I make this like twice as much, then 2 squared is 4. So you'd have 1/4 the force. I hope you can kind of do that kind of stuff. Relationships between different things. Some people thought that gravity was rather local, and some evidence for that was back in the early 1700s when they looking at the planets. The astronomer types know that when a planet goes by Jupiter, for example, the planet coming around the sun like this, when it goes by Jupiter, it sort of wobbles a little bit. And that was to be expected, because it's an interaction between the planet and Jupiter too, like the planet Uranus, okay? But when Uranus is way out here, and Jupiter's over here, they found out that Uranus was acting a little differently out there too. They call that a perturbation. And they found out that the planet Uranus was undergoing a perturbation where no other planet was. And the popular idea at the time was, well, way out there, the law of gravity, Newton's majestic law of gravity, is obviously breaking down. But not everyone believed that. A couple of mathematician types made some calculations as to where another planet would have to be to cause those perturbations. And they made about the same time in history. One was an Englishman, the other one was a Frenchman. And the Englishman reported his hypothesis and sent it to the observatory in Greenwich, England. When the observatory types got his letter, opened it up and says, "What's this? Some mathematician is telling me that there's a new planet, so-and-so coordinates in the sky. What is this stuff?" I'm exaggerating. The Frenchman sent his findings to the observatory in Berlin. And the Berlin types said, "What's this? A new planet? If I turn my telescope so many degrees that way and so many degrees, I will find a new planet?" Son of a There it was. They discovered a planet predicted by the law of gravity. And that planet they called Neptune. That's right. Neptune was predicted. That's the nice thing about science. If you know some science, it will allow you to predict things, see? And they predicted where Neptune was. Ain't that neat? And later on in 1930, this century, they found other perturbations of Uranus. And those other perturbations led to the discovery of what planet, gang? You know? Pluto. That's right, Pluto. And Pluto was predicted before it was discovered. And it's awfully hard to find those little specks in the sky. And kind of neat. Let's be talking about this becoming an exact equation. You see, this reads the force is proportional to the masses and the distance squared. But in your textbook, you see the equation written like this. What's the G? The G relates the force and the masses and the distance squared, so that this is in newtons and these will be in newtons also. And you know how G was found? It wasn't found by Newton. It was found much later. It was found, I think, in the early 1800s or early 1700s. Now, I should be knowing that, gang. But it was found by a fellow by the name of Cavendish. And he had kind of a neat way of doing it. And someone shortly after that, by the name of Philip Van Jolly, found an even simpler way to find what G is. And here's what Van Jolly did. Van Jolly had a mass that was balanced with a known mass over here. Underneath this mass, he rolled 6 tons of lead. And that's M2. And he knew this very, very accurately. And he knew this very, very accurately. And when he did that, guess what happened, gang? This side pulled down a slight bit. It got out of equilibrium. So what Van Jolly did was he put some other little masses on here. Now, we didn't have this equal like this, because, I mean, you couldn't see the darn thing. Yeah? Okay. But he put some other little masses there and restored the balance. When he put the other little masses here to restore the balance, that's to say he has the force that pulled this down. He knows the force. He knows the mass. He knows M2. And he could measure the distance very accurately. He has everything except G. All he's going to do is take that force, numerical value, divided by the product of the masses, divided by the distance squared. And when he did that, he got a tiny, tiny number. 6.67 times 10 to the minus 11. That's not like, that's a lot different than 22 sevenths, huh? 6.67 times 10 to the minus 11. That is what he got for the ratio. And you know what? Change the masses, put a bigger one, a small one, make no difference, change the distance. You'll always get the same ratio of force to mass over distance squared. Just as you'll always get the same ratio for big circles, circumference to diameter, circumference to diameter. So this is the constant of proportionality. We don't call it pi, gang. Guess what we call it? G. See? That's not called pi. That's G. Big G, right, big G. And so we can say, now we have the exact equation. F equals G, da, da, da. When this experiment was done, the science writers correctly interpreted it. They said Cavendish, who did it first, has just measured the mass of the world. Because see this piece of chalk? Can you measure the mass of that chalk? Yes. Do you know the distance between it and the center of the world? Yes. Do you know the G constant? Yes. Can you get the force? Yeah, put it in a bathroom scale. You got that. What don't you have? The mass of the world. And at that point, then one could calculate what the mass of the world is. And that's wild, because when I was a kid and I was told that the science types knew what the mass of the world was, I say, including the mud puddles they don't know about in Ceylon, including the sticks and stones and the elephants they don't know about up in India, including all the lava that they don't have a good handle on way down underneath, and what's at the center of the world, they know what that is too? How do they know such thing? They be knowing such thing, honey. Because one left. That's the mass of the world. Ain't that neat? Next time we're going to be talking about ocean tides. And we'll be talking about ocean tides. We're going to be talking about the role that the moon plays when it pulls on the oceans of the Earth. Okay? But let's talk a couple of things about the moon now. You probably all know that there's only one side of the moon that can be seen from the planet Earth, yeah? You look up and there's one face looking at you all the time, all right? Now, why is it that one face is looking at us all the time? Some people will say, well, the fact that one face is always looking at us, and it wasn't until the astronaut types went out and looked at the other side that they knew, you know, what, maybe it was a great big, it could have been anything back there, like a great big plastic mold, to entertain Earth types, maybe like a Hollywood set in the back there. And they went back and they found the other side was pretty much the same as this side. The Russians were the first to do that, and US types right after that, yeah? So we know we do have a world with two sides. But nevertheless, one side always faces us. Now, the popular thinking is, the fact that one side always faces us is evidence that the moon does not spin about its axis like the Earth. We know the Earth spins about its axis. We know that. It turns around, round, round, okay? And it makes one turn every 24 hours. The sun's up here, we get what, day over here, and we get night and day and night, right? Isn't that true? Okay? We know the Earth is spinning. Is the moon spinning similarly about its axis? Take a stab at it right now with your neighbor. Yes? No? I don't know, but I'll take a guesstimate. That guesstimate will be called a hypothesis. Go. How many say, I think that the moon is spinning like a top as well? Show of hands. How many say, no, I think the Earth might be spinning like a top, but I think the moon is frozen so that it doesn't spin at all? Show of hands. How many say, well, I saw a lot of hands up before, and I kind of think that, but I ain't going to put my hand up, because someone might know I'm wrong. It'd be terrible, right? That reminds me of the time I was roller skating, man. I used to be a roller skate freak. Oh, I loved to roller skate. I wish you guys had a roller skating rink around here. But I'm skating at the rink, and one day I'm skating with a lady, I'm skating with her, and you go a bit, where are you from, what's your name, da-da-da, all this bit like that, And she volunteers some information to me. I said, how long have you been skating? She said, I've been skating 9 months. And she says, and I haven't fallen down yet. She was very proud of the fact that she had never fallen down. I said to myself, honey, you can't skate either. She couldn't skate with a darn, okay? She club, 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 being very, very careful. And she went 9 months without falling. She thought that was an achievement. And you know what all the honchos in the rink? the honchos in the rink gang, they're all rosin all over their bodies. All smeared with it. Every time you fall down, you slide in the rosin, see? And the honchos are falling down all the time. You try this spin, you try this jump, you fall down, you get up, you keep going. And this lady thought it was an achievement that she never fell down. How many of you guys will go through this course and at the end of the course say, you know what? I never volunteered a wrong answer to my neighbor, not once. Of course, I didn't learn anything, but I never fell down. Okay. Do you guys have a hang-up about saying something that might be wrong? Huh? Don't, come on, it's okay. It's okay to be wrong. You got to keep falling down. If you don't fall down here, you can't skate. Huh? So learn how to skate. It's okay to fall down. It's okay to be wrong once at a time. But anyway, let's get back to this idea here. Here's an eraser, and we are on the moon. And let the eraser be the moon. And we can read this side, can't we? This is the side that faces the Earth. Okay? This side faces the Earth. And doesn't the moon go around the Earth? Well, watch how the moon goes around the Earth. What am I doing to the eraser, gang, as it goes around the Earth? I'm twisting it. Because it turns out the eraser is going like this as it turns. And when it makes one turn like this, it'll also make one rotation. So it'll go, and all if it stopped it, it would just keep. Stop it for a minute. You didn't need? So the moon is turning around and around and around. And you know what? There's a reason why one side always faces us, and it have to do with center of gravity and torques. Did you pick that up in the chapter on rotational motion? Did you pick that up? And when you picked that up, did you say to your mother and father, hey, you know what I just found out? There's a reason why one side of the moon faces us all the time. How many people did share that with their parents? How many say, well, my parents don't give me anything, I'm not going to give them anything? do you people share these ideas with the people at home? How many of you people do share these ideas, some of these ideas, with your friends, your family, or someone you care about? How many do? How many say, not me, it's mine, I paid my tuition, no one's going to get it? No, you got to share these ideas. Hey, here's a neat one, gang. Get this one. Here's how it goes. Let me get this out of the way a little bit. This one I get kind of excited about. Here's the Earth down here. And here's the moon. It turns out the moon up here gets pulled into kind of an oblong shape. We'll get into this when we get into tides. It turns out that this side is closer to the Earth than this side. And this side gets stretched out. So it kind of stretches into that shape. Okay? That's the whole tide bit we'll talk about next lecture. Let's suppose the moon is like this. Well, the center of mass of the moon, about which rotation takes place, is right there. But the center of gravity of the moon isn't there, because this part here is being pulled with more gravity than this part. Why? Because it's closer. Inverse square law. Over here is being pulled harder than here, right? So what happens is the center of gravity is about there. And so the Earth is pulled as if all its mass is there. But it's rotating about this point. There's a line joining the two centers. What's this little distance right here called, gang? Begin with L-A. That's your lever arm. So you got a little lever arm distance and you got a force. When you got a force through a lever arm, that gives you a torque. And so a torque produces a what? A rotation. And so what it does is it rotates down like this. Now if it overshoots to the other side, which way is the torque tend to rotate it now? Back. So it whoop, 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 shunk, like a compass needle in a magnetic field. It'll line right up with a field. You know a compass needle? One needle's being pulled like that, one's being pulled like that, and they kind of boom, pull into straight. And it straightens right out. And a compass needle will line right up with a magnetic field like this, huh? The moon lines up with not a magnetic field. What kind of field? The gravitational field. Because surrounding that world is a gravity field, honey. And that moon is out in it. And what happens is this lines up, so it lines up, so both those centers, here's the condition of equilibrium, one that acts right through there. What's the torque when that force passes right through the center of mass? Begin with a Z, end with a P. Zip. No torque, no torque, no what? So what it does is it hangs right in there. So it's not a coincidence that the moon has one side frozen to us. It is not a coincidence. In fact, when we go out and look in the solar system, you'll find out things have been orbiting around long enough will eventually face each other and be frozen. That's the normal state in the universe. And even the Earth is approaching that. One day the Earth and the moon will be locked on each other. And that day is coming. Not for a while, so you can kind of live it up. Okay? I want to ask you a question that next time when you come to class, I want you to have it. It's a question you can ask your friends at home and you'll get a variety of answers, but you will know the answer. And here's the question. We all know that the moon is tugging on the oceans of the Earth. We all know that. We call that tug a what? The force of what? Gravity, right? And we know that force of gravity have to do with tides, right? Okay? We all know that the moon is pulling on the oceans of the Earth, right? Because the moon has a mass, the oceans of the Earth have a mass, there's a distance between, there's a force there as well. I got a question for you. Which do you suppose pulls harder on the oceans of this Earth? The moon or the sun? I want everyone to come to class next time knowing that. And guess where you can find the answer if you're not sure now. Guess where you can find it, gang. Begin with B and with ook in your book, okay? So next time, let's come in knowing that. E, physics, huh?